Thank you. Can you hear me? All right. So let me join the other speakers in thanking the organizers for putting together such a wonderful conference and for inviting me to speak. I'm going to present some work in collaboration with Po Shen-Sin, who was a postdoc at UCLA, is not King's College. This talk is about phases of gauge theory. So let me flash for you some of the kind of quintessential examples of gauge theory phases. There's electromagnetism, Coulomb phase of U1 gauge theory. For today's talk, I'll be interested in QCD, so we'll discuss the confining phase of SU3 color gauge theory. There's the electroweak theory, which is a quintessential example of a Higgs phase in particle physics, and in condensed matter physics, we encounter similar Higgs phases in the context of superconductivity when the U1 gauge group is Higgs down. And in all of these examples, one needs to take the word phase with a grain of salt. And in order to be more precise, as you learned from Sakura, you need to be careful about what kind of order parameters and what kind of symmetries you use to define your phases carefully. And this is an old idea that goes back to Landau. And so loosely speaking, we'll refer to it as the Landau paradigm. So in the context of gauge theory phases, we've known for a long time that the correct order parameters are not local operators, but they're loop order parameters. In the context of 4D gauge theories, they can be electric or magnetic loops. For example, here I've drawn a loop over there. And the question of what is the global symmetry under which these loops are charged is, in a sense, a very old question that has been partially answered for a long time, but sort of has come into its own more recently with the notion of one-form symmetries, which are the sort of fully covariant versions of things like center symmetry that act on loops. So just to give you an example, which again will be important for the talk, if we consider pure SU3 gauge theory without any matter, then that gauge theory has a Z3 one-form symmetry because the center of SU3 is Z3. And under this Z3 one-form symmetry, the fundamental Wilson loop is charged. It acquires a Z3 phase under the action of the symmetry. And if you're in the vacuum, where the theory confines, then famously this loop, when you make it very large, decays exponentially fast. This is this famous area law decay of the Wilson loop. Sigma here is the confining string tension. So it decays to 0. That means that the symmetry is unbroken in the vacuum. That signals confinement. And if instead you heat up the theory by putting it at finite temperature, then at some point you will reach the deconfinement transition. And in the high temperature phase, the Z3 symmetry is spontaneously broken. So here in the pure gauge theory, we have a completely sharp story involving symmetries, order parameters, and transitions. Let's see what happens when we add fundamental matter. So it's completely generic that when you add fundamental matter, the electric one-form symmetry that I was just talking about is explicitly broken. The presence of one-form symmetries, whether they're electric or magnetic, always requires non-generic matter content. All right? So in particular, I'll be discussing QCD with fundamental quarks, so normal QCD. This does not have a center symmetry. That's well known. And the consequence of that is that if you have a Wilson line, like the one I was using as an order parameter before, you can simply put a quark or an antiquark at the end, and physically the stable confining strings of pure Yang-Mills theory can snap open. They can break. So famously, QCD with quarks doesn't have completely stable strings, and that's not just some random fact. It has sharp consequences for the phase diagram. For example, if you heat up QCD with physical quark masses, then there's no sharp finite temperature deconfinement transition. Instead, if you study that theory on the lattice, I guess my pointer is only over here, then you find a smooth crossover as a function of the temperature. All right. So I discussed a little bit the finite temperature behavior, but there's a kind of version or an avatar of this fact that gauge theory of fundamentals doesn't have a one-form symmetry, which is in the context of the Higgs phases of the theory. And this goes under the general slogan of Higgs confinement continuity. If instead of quarks you add fundamental Higgs fields to gauge theory, if you add enough of them, then you can completely Higgs down the theory to nothing, and you get a trivial gapped vacuum, which looks very much like the confining vacuum of the theory. And because there's no one-form symmetries once you've added the fundamental Higgs fields, there's no order parameters, no sharp notion of phase that you can use to distinguish the confining and the Higgs regime. And this leads to the idea that those two regimes should be continuously connected without a phase transition between them. And this is not just a kind of general principle. It comes from rigorous results. For example, there's a famous set of rigorous lattice results by Fradkin and Schenker and by Banks and Rabinovich, which kind of started this whole business. And over the years, it's been observed to be a feature of many, many models that can be analyzed exactly, especially models with supersymmetry, where you can often tune moduli continuously to take you from what is ostensibly a Higgs regime to what is ostensibly a confining regime. So this is, kind of, these are some of the basic ideas that sort of underlie this Higgs confinement continuity dogma. And what I would like to talk about today are a series of simple examples in 3+ 1-dimensional gauge theories, including real QCD, where this dogma can fail. And it fails for a simple reason, which is related to something that you already heard from Sakura about. I'll focus on two very simple examples just to explain them in the talk. There are many more. The mechanism is pretty generic. It works in any dimension. And as we'll see, this will lead to unexpected kind of non-Landau type Higgs confinement transitions. And the underlying mechanism will be that in these examples, the Higgs regime and the confining regime will actually be different symmetry-protected topological phases for some global symmetry. It won't be a one-form symmetry, but there'll be some global symmetry. And in the second half of the talk, I'll discuss some applications to QCD at finite baryon density. All right, let me flash briefly or remind you what an SPT is, especially with an emphasis on the thing that I would like to use it for, which is to diagnose the presence of phase transitions. So SPTs are kind of all over the place, but in their modern, useful incarnation, they certainly come from condensed matter physics. Things like the integer quantum Hall effect and topological insulators and superconductors, which are the things that we'll discuss. And from a quantum field theory point of view, you can think of SPTs as anomaly inflow theories for background fields. If you have a global symmetry, then you can put some background fields for that symmetry. Then you can write an anomaly inflow action for those background fields. And the SPT is the theory that lives in the same dimension as the anomaly inflow action itself. And at least in the relativistic case, SPTs are some of the best understood, mathematically best understood quantum field theories as well, because they're rather simple. So a simple warm-up example, just to jog your memory, is a 2+ 1-dimensional theory with a U1 symmetry and a background Chern-Simons term. So this is a non-dynamical Chern-Simons term, which captures some kind of response. And here you have a quantized coefficient k. And the main utility of this quantized coefficient is that it can diagnose phase transition. So if you dial the parameters of your system and the coefficient somehow jumps, and you can show that, then you can argue that the two phases where k takes different values, different integer values, have to be separated by a phase transition. The phase transition could be first order, it could be second order. You don't necessarily know much about it, but you know that it has to exist. One small thing I want to emphasize, which will be important shortly, is that in Euclidean signature, this Chern-Simons term has an I. That means that it contributes to the phase of the Euclidean partition function. That's pretty typical of SPTs, and we'll see in a second why that's important. All right, so the talk will be about gauge theories in 3+ 1 dimensions. So let me remind you of a simple example, which will also feature the basic SPT that will be our main workhorse. There are many others. Let's consider a free two-component fermion, a Weyl fermion. So I'm using Wesson-Bagger notation here. So alpha is a two-component spinor index. And here's a free fermion Lagrangian with a mass m. In general, m can be complex. But if you insist on time reversal symmetry, then m is actually forced to be real. And now we would like to study this theory as a function of real m. So if m is non-zero, the theory is gapped. And moreover, if you are kind of naive about it, you would say that the theory for positive and negative m looks exactly the same, because there's an axial symmetry that relates those two masses. But one has to be a little bit more careful. If you study the theory in the presence of background fields, you find that the U1 axial actually has a mixed anomaly with gravitational backgrounds. And that means that the two phases, the positive and negative mass phase, actually are slightly different. They differ precisely by the presence of an SPT. And in this case, the SPT is a gravitational theta term. Here it is. I've written it in units in which the theta angle has a conventional periodicity 2 pi. And what you'll find is that in one phase, theta equals 0, and in the other, theta equals pi. And those are the only two values that are compatible with time reversal symmetry. And the fact that the SPT jumps means that you necessarily have to have a phase transition at 0 mass. Here, that's kind of trivial because the 0 mass point is also the point where the fermion comes down and gives you a second-order transition, but more generally, it could be a first-order transition. And notice that time reversal is absolutely crucial here. Without time reversal, you could take the fermion mass to be complex, and you could go from positive to negative m without ever encountering the origin. All right. So I'm interested in QCD, and I'll be studying the kind of physically relevant case where all the quarks have positive masses, and the theta angle is basically 0. We know that that's true to an excellent accuracy. And it's known that you can write down the QCD path integral in such a way that the Euclidean path integral measure is positive definite. This is a famous result due to Waffe and Witten in the continuum and Weingarten on the lattice. And this has many important consequences for the dynamics of QCD. And one consequence is that if you integrate a positive measure on some manifold, you get a positive number. And that means that the partition function of QCD with positive quark masses is always going to be a positive number. And I've told you that SPTs give you non-trivial phases in the partition function. Therefore, all of these path integrals give you trivial SPT phases. So you have to do something to QCD to make it spit out a non-trivial SPT. And we'll do two such things. We'll add Yukawa couplings by hand in one model. And in the other model, we'll turn on a chemical potential. Another option is to consider the case of negative quark mass. That was done by Tachikawa and Yonekura a few years back. But I will not consider that here. All right. So here's my first example. I'll call it Higgs-Yukawa QCD. It's a kind of deformation of QCD by adding in some extra fields. So I'm going to start with ordinary QCD, familiar SU3 gauge theory. I'm going to add 3 flavors of quarks. I'm going to take 3 Dirac quarks, which I'll write as Weyl pairs. So here psi and chi are my 2-component Weyl fermions. A and I are color and flavor indices, which in this case both run from 1 to 3. And for simplicity of the presentation, I'm going to take a common positive quark mass. So that means that in addition to baryon number, I also have an SU3 flavor symmetry, which rotates the quarks. And then I'm going to depart from normal QCD by just throwing in an extra Higgs field by hand, an extra elementary Higgs field that I call H. H here is a bifundamental or a bi-antifundamental of both SU3 color and SU3 flavor. And I can add a bunch of interactions for H. First of all, I can add a potential. I'm not going to write it out explicitly. I'm just going to tell you what it does. And then I'm going to add, very importantly, a Yukawa coupling. And remember that a Yukawa coupling was one way to generate an SPT. And I'm going to write the following Yukawa coupling, which, as you see, contracts the flavor and color indices in a kind of fully antisymmetric fashion. So this is gauge and flavor invariant. It also preserves baryon number, if you assign some baryon charge to H. And finally, if you pick precisely this combination of psi and chi, you also preserve time reversal and parity. And if you imagine what adding this little Higgs to the theory does, it leads to an interaction between quarks, which is attractive in the color flavor antisymmetric channel. That's precisely the same channel that is attractive in real QCD with gluon exchange. So that'll be important a little bit later. OK, so let me study the phases of this theory. So first, I'm going to take the Higgs mass to be very large and positive. Then I can just forget about it, integrate it out, and I'm back to ordinary QCD with a positive quark mass. And remember that I was using conventions in which that was a gapped and trivial SPT with positive partition function. The interesting case is when I take the Higgs mass to be very large and negative. So now I'm deep in the Higgs phase. I haven't told you what the potential is, but I'm going to pick it in such a way that I engineer the VEV that I want. And in this case, the VEV that I want takes this particular form. This is called a color flavor locking Higgs VEV. And you see that what it does is it ties the color and the flavor indices on H together with a delta function. That has the interesting feature that the gauge group is completely Higgsed, so the gauge group is gone. And on top of that, the flavor symmetry, the SU3 part of the flavor symmetry is unbroken because of this diagonal identification. So there are no Goldstone bosons for SU3. There is a Goldstone boson for the U1 baryon symmetry, because it turns out that if you take the determinant of this H, which is invariant under the SU3s but has baryon number 2, then that gets a VEV, and the U1 baryon number is spontaneously broken. That means you get a single massless Goldstone boson, and otherwise the theory is gapped. OK, so the Higgs phase is gapless. There's a Goldstone boson. And on top of that, I want to figure out if the Higgs phase can be a non-trivial SPT. I want to figure out if the gravitational theta angle is 0 or pi. Now, whenever you have SPTs are most robust when the theory you're studying is gapped. Whenever there's something gapless, you have to be a little bit careful, because in principle, the gapless thing can make the SPT ill-defined. And this could happen, in this case, if there was a mixed anomaly between U1 baryon number and gravity. And then the Goldstone boson could actually absorb the SPT. But baryon number is a vector-like symmetry, and it does not have such a mixed anomaly with gravity. So we're safe, and we can calculate the value of the gravitational theta angle. That's easy to do. We just need to diagonalize the fermion mass matrix in the Higgs phase. So what we're going to do is we're going to split up the fermions under the unbroken flavor symmetry. There are 9 psi's and 9 chi's, and they both split up as a singlet and an octet under the SU3. And then when you plug in the Majorana masses coming from the Yukawa couplings, you see that the bare quark masses get modified. There's this kind of like off-diagonal plus-minus structure, which comes from the Yukawas and the Higgs VEV. And there's factors of 2 and 4, which have to do with the symmetry breaking pattern. So what you see from these formulas is if you make the Higgs VEV very big, if you're deep, deep in the Higgs phase, then half of the fermions acquire a plus sign, and half of the fermions acquire a minus sign. And since there are 9 plus 9 two-component fermions to begin with, it means 9 of them have flipped sign. And that means that the theta angle has jumped an odd number of times, and you end up in the non-trivial SPT with theta equals pi. All right, so what is the phase diagram of this model? Well, we have the positive Higgs mass phase where everything is boring and trivial, no SPT, no symmetry breaking, etc. And then we have the Higgs phase, where we have both symmetry breaking, the U1 baryon number is broken, and on top of that we have a theta equals pi gravitational SPT, topological superconductor. So now we have an abundance of riches. We have two different regimes, and we actually have 2 independent arguments why those 2 regimes should be separated by a phase transition. Right? The first argument, it just involves the realization of baryon number. In one phase it's unbroken, and in the other phase it's broken. So even Landau would have told us that there should be a phase transition in between. There has to. And on top of that, we also concluded that the SPT jumps. So that's yet another kind of non-Landau reason why there has to be a phase transition. And the question is, are those 2 arguments related, or are they kind of decoupled from one another? So basically, I'm asking, is there one phase transition, or are there 2? And I would like to convince you that generically there should be 2 phase transitions. So let me decouple those 2 phenomena for you. In this model, nothing is stopping me from explicitly breaking baryon number, and I'm going to do that by adding the order parameter of baryon number breaking. This is the operator that got a VEV in the Higgs phase. So if I turn it on with a small coefficient, I break baryon number explicitly. Now the Goldstone bosons are gone in the Higgs phase, and the phase diagram looks a little bit different. Notice that, by the way, this preserves still, very importantly, parity and time reversal, so the SPT is unharmed. I'm lifting the number of Goldstone bosons, so now both the Higgs and the confining phase are gapped and trivial. So if we didn't know about the SPT, we would have concluded that they're both featureless and they both look identical, so they're probably the same phase by Higgs confinement continuity. But in this case, we know for sure that they cannot be the same phase, because the SPT still jumps. So in this example, the SPT forces a unexpected Higgs confinement transition, which is generically distinct from the symmetry breaking transition. You're going to show me 10 minutes?
You have 6 minutes.
I have 6 minutes, OK. So the answer is yes. So let me go to my second example, which, as you will see, is related to the previous one spiritually. And now I'm discussing honest-to-God QCD. I'm not throwing in my Higgs field anymore, but I am turning on a chemical potential for baryon number. So I'm studying finite density QCD, and I'm going to take the same setup, 3 light quarks and degenerate positive quark masses. So this SU3 symmetric case is much easier than the sort of real-world case with the physical quark masses, which is very complicated. And in this case, the phase diagram is believed to be fairly simple. There's a low-density regime, which is gapped and confined. And then it's believed that there's basically a single phase transition somewhere around here at baryonic densities, at nuclear densities, where the baryon number symmetry is spontaneously broken. So you enter this baryon superfluid phase. And this happens sort of at sufficiently low densities that you should call it a confined regime. And then it extends all the way to a Higgs regime, which I'll review. And this whole phase here has U1 baryon broken. Now, Schaefer and Wilczek in the 90s basically proposed that this is an example of Higgs confinement continuity, and that in this baryon superfluid phase, there shouldn't be any additional phase transitions. So let's look at this model from the point of view that we've been taking. Let me analyze the very high density regime. The very high density regime is under excellent theoretical control, thanks to a lot of important work in the 90s, starting with this paper by Alfred Rajagopa and Wilczek. When you're at very high densities, QCD is essentially weakly coupled, and you can more or less work out what it does. I'm slightly oversimplifying here, but what basically happens is that you have a huge Fermi surface for the quarks, and then there's BCS pairing at the Fermi surface, which is, in first approximation, just mediated by one gluon exchange. And this one gluon exchange acts in exactly the same color flavor antisymmetric channel that we already played with in the other model. So what it does in this model, it leads to a color flavor locking VEV for a Higgs field, but it's not an elementary Higgs field that we threw in by hand. It's this composite paired quark-quark Higgs field, which has exactly the same quantum numbers as before. So therefore, the consequences are also basically the same. The two Higgs phases that I described are basically qualitatively identical. For example, the gaps in QCD have this structure with the same relative factor of 2 between them. And the symmetry breaking is the same, and the fact that there's a Goldstone boson is the same. So we can ask ourselves, are the SPTs also the same? Oops. Well, I claim that the answer is yes. I claim that the SPTs in these two weakly coupled Higgs phases are both given by theta g equals to pi. And you can explicitly prove this by constructing a deformation that interpolates from the Higgs phase of the model I discussed first, which had the elementary Higgs field but was at 0 density, to real QCD at finite density but without the elementary Higgs field. And this interpolation path always keeps the fermion masses non-zero, so it doesn't affect the SPT. Thank you. All right. So now we conclude from that high-density QCD is, in fact, a gapless SPT, an example of a gapless SPT, which Sakura mentioned in her talk. So the U1 baryon symmetry is broken, and we have a Nambu-Goldstone boson for that. And on top of that, we have theta equals pi. Now, based on what I told you in the other model, you should assume that generically these two effects, U1 symmetry breaking and the SPT jumping from 0 to pi, are decoupled from one another. So that means that this picture motivates new unexpected phase transitions also in the finite density QCD case. So in other words, whereas the original picture was that at low density you had a trivial phase and then eventually there was a symmetry breaking phase transition to the superfluid phase, here I'm proposing that the jump of the SPT generically should lead to yet another phase transition somewhere in this superfluid phase in tension with this conjecture by Schaefer and Wilczek. All right. And let me just briefly comment what the presence of this SPT might imply for neutron stars. If you are a deluded theorist, you might think that the cores of neutron stars are so dense that eventually you're going to get to this very weakly coupled Higgs phase where theta equals pi. It's not clear if that can actually happen, but one can hope. And if that happens, though, then you can say for sure that the picture will look something like this. You'll have a phase in the middle, which is the dense Higgs phase, where theta equals pi. And then in the outside, you'll have a phase where theta equals 0. And just anomaly inflow arguments associated with the SPT tell you that there have to be some kind of anomalous edge modes on the boundary layer separating those two regimes. The simplest anomalous edge mode could just be a gapless fermion, but there are also more exotic examples like various anion models. All right, so that brings me to my conclusions. So the main slogan of the talk is that Higgs confinement continuity can fail if the two regimes are in different SPT phases. And even though I've focused on two simple examples, this is a very general trick that works in many examples. And one of the claims that I tried to justify for you is that high-density QCD is, in fact, a gapless SPT with a gravitational theta angle pi. And as I briefly sketched, this should have real consequences for the QCD phase diagram and very optimistically maybe also for neutron stars. And the last comment is, well, motivated by the fact that we're at a strings conference. So I started the talk by saying that QCD with quarks doesn't have any stable strings. But that's not 100% true, because I told you that dense QCD was a U1 baryon superfluid. And if you start spinning up that superfluid like you do in the core of a neutron star, then there are vortex strings. And those vortex strings are somehow the distant cousins of the QCD strings. And I think it's an interesting open question to what extent their physics is affected by the SPT that I discussed. So let me stop here. Thank you.
Thank you very much, Thomas, for your excellent talk. Questions? Please use your microphone.
Hi, thanks for the nice talk. So for your model or for real-world QCD, do you have any indication of whether this 0 to pi phase transition is first or second order?
Well,
yeah.
No.
Okay.
In general, the answer is no. There's a limit of my model, which is the limit when the quark masses become very large, in particular much larger than lambda QCD, in which this transition happens deep in the weakly coupled Higgs phase. And then it's second order, plausibly.
I see. Yeah, and maybe like a more modest question is like, do you have a general idea, either in QCD or your model, like how this transition, or basically what this map would look like also in the temperature direction?
No. If there are phase transitions at 0 temperature, then generically they have implications for the finite temperature phase diagram. But the SPT itself is something that only makes sense at 0 temperature. It actually becomes unstable at finite temperature. Yeah.
Yes.
If someone can bring me a microphone, otherwise I'll speak into this one. But if I speak into this one, I'm looking away from you. I'll do the best I can. So thank you for this great talk and the presentation of color flavor locking and its consequences. I'll make two comments. One is about real-world neutron stars, and the other is about the three-flavor model. So for real-world neutron stars, there's growing evidence from the combination of LIGO and Virgo data, perturbative QCD calculations that are quantitatively valid at about 40 times nuclear density, and X-ray data from X-ray satellites on neutron star radii, that two solar mass neutron stars do have quark matter cores. The problem for us theorists is that in the real world, the strange quark is heavier than the other two, as you said, and so I think it's very exciting that there is quite plausibly in neutron stars that exist in the world quark matter cores, but they're probably not CFL. So it's probably not. It would be great. Your picture at the end would be magnificent, and we can still hope for it. And I think this is worth paying attention to. But it's probably quark matter that's not CFL, and we can talk afterwards. What I wanted to say about the three-flavor model, which you worked in, I think you and we understand the high-density CFL better than we understand that intermediate regime. So the intermediate regime, it's a three-flavor world. So it's baryons. The intermediate regime is superfluid baryons, but it's not just neutrons and protons. It's an octet of baryons. So you have 8 baryons and superfluidity breaking the U1. My suspicion is that that's the phase we don't fully understand. the high density phase where the CFL pairing comes from. So I would suggest that we all have to think carefully about that superfluid baryon phase and ask whether we understand that completely, taking into account all the possible patterns of pairing among the 8 baryons, which I don't think has been fully done because sort of real world physicists focus on, like people who study real neutron stars focus on just the neutrons. But when you have 8 baryons pairing, there are other possibilities which may or may not restore Schaefer and Wilczek's original speculation. I will say that immediately after Schaefer and Wilczek, we pointed out that this is completely unlikely in the real world because of the strange quark mass. If you look at the set of things that have to happen to get from neutron matter up to CFL, there's a lot of things that have to happen.
Absolutely. Thank you, Krishna.
Quick response?
I'll try to give a quick response. So on the first point, I would love to hear more about the neutron stars. About the second point, about the baryon pairing, you're completely right that we know very little, even in the 3 flavor, in the degenerate case. But I think we know something, which is the thing you started with, which is that the baryons are in an octet. And the fact that there's 8 of them, rather than the 9 quarks, which were responsible for giving me the SPT jump, means roughly speaking that any pattern of baryon pairing involving only the octet at nuclear densities, at baryonic densities, is unlikely to give you this SPT jump. So this means that whatever happens, it's likely that the SPT jumps somewhere in the middle of this phase.
So we should talk, because what we did immediately after Schaefer and Wilczek was to show how you have to go from 9 to 8. We'll continue this conversation after.
Okay,
Great, thanks.
I think there were further questions.
There's one more question over there. Igor?
Igor, yes.
Yeah, thanks for a great talk. Sometimes people contemplate phases where translation symmetry is broken, maybe at intermediate phases. Have you thought about this?
Not as much as Krishna, but a little bit. As long as time reversal symmetry is unbroken, the fact that translations could be broken do not spoil the SPT. So in fact, there are many quintessential examples of SPTs, like the B phase of helium and things like that, where there's some kind of space-time symmetry breaking, and on top of that, there's an SPT. So these things can coexist. And in the spirit of what Krishna said, people have really studied the hell out of all these different phases, and I think it's really interesting to try to figure out where the SPT might plausibly jump.
Well, I'll just say that's generous of you, but I think we really got stuck on Igor's question. There's a lot of literature on crystalline color superconductivity, but I think it leaves many questions still open, which are worth thinking about.
Let's see if there's a final question. Yes, please.
Was SU3 important for your story? Could you do SUN and in particular large N for this?
Color, yeah.
Yes, color and flavor.
Yes, you could do both. So in the case of the model with Higgs fields, you can do this, and you can write down different generalizations, and you can work out the symmetry breaking patterns. At the level of this is basically a free fermion calculation. The finite density case is a much more chaotic system as a function of n and nf. So only the low-lying cases have been worked out, and it's been seen that the patterns of symmetry breaking and the phases you get are not particularly uniform in NC and NF. So,
okay.
Yeah.
So there's no simple large N limit for this story?
People have thought of the large N limit, and it's considered to be complicated and possibly plagued by instabilities and so forth.
Thank you.
Yeah.
Okay, I think in view of time, we thank Thomas again.
Thank you.